We have another snow day this morning, so I'm going to continue with section 4.4. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there is a rectangle whose area is precisely equal to the area of the region under the curve. So let's take a look at this graph here. We can take the integral of f and figure out from a to b and figure out the exact area underneath this curve. There is another way to be able to do that as well, and it's called the mean value theorem for integrals. And what that means is there has to be some value in between a and b such that if I substitute c into my function to get my height, and I multiply that by my b minus a, so the change in my x, I should be able to get a value that's equal to the area underneath that curve. So this area of this rectangle here would be equal to the area underneath this curve. So I'll give you a minute to write down, this is the formal definition of the mean value theorem for integrals. If f is continuous on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the integral from a to b of f of x dx is equal to f of c times b minus a. So this area right here is just the area of this rectangle right here. The value of f of c is given by the mean value theorem for integrals. It has a name. It's called the average value. Okay, so we are looking for that height. Okay. Definition of an average value, you can go ahead and write this down. If f is integratable on a closed interval from a to b, then the average value of f on that interval is given by this. So we still take the integral from a to b, but to find the average value, we will take that and multiply by 1 over b minus a. Okay, so that's basically giving us the average value. Let's go ahead and do an example on this. I want you to write down this example. We are going to find the average value of f of x equals 3x squared minus 2x. And we're doing this on an interval from 1 to 4. So this is our average value formula. We're just taking the integral of this function from 1 to 4, but then we're going to multiply by 1 over b minus a. So here I've substituted in my function for f of x. Don't forget your dx. We're going from 1 to 4, and it's 1 over b minus a, 4 minus 1. In this next step, I have that 1 over 4 minus 1 is 3, and I haven't done anything else to this point. In the next step, I go ahead and take the integral. So to take the integral, I'm going to add 1x to the exponent here, so this exponent becomes a 3, and then I will divide by the exponent, which is what gets rid of this 3, minus, and the integral of 2x is going to be x squared, and we're evaluating from 1 to 4. Because of that fundamental theorem of calculus, we know how to do this the quick way. First, we will substitute 4 in for our x's here and here, and then we will subtract that same product by substituting in 1 into here and get 0. So we have that 4 cubed is 64, 4 squared is 16, and when I multiply all of this, I end up getting 16. So let's take a look at the graph here so that you can get an idea of what this is actually doing. Okay, so here's our function. We are evaluating from 1 to 4, okay, and we're not evaluating the area in this case. We want to know what the average value is. And so if we were to take the area here and we were trying to compare it to the area of perhaps a rectangle that was equivalent to that area, that f of c point, which is this point right here, 16, that y value is what we just found. So the average value in this situation is 16.